Hello, and welcome to today's PSU Transportation Seminar. My name is Leming Wang, and I will be introducing and moderating today's seminar. Excuse me. On Friday, our Friday Transportation Seminar has been, has been a tradition since the year 2000. And these seminars are usually held live on Portland State University's urban campus, located on the ancestral homelands of the Monoma, Cathlamet, Clackamas, Tumwater, Guadalala, bands of the Chinook, the Tualatin, Kalapuya, and many other indigenous nations of the Columbia River. It is important to acknowledge that we are here because of the sacrifices forced on the indigenous ancestors of this place. Remember these communities and to honor their legacies, lives, and descendants. Today, we are pleased to have Milad Ashtiani.
Almost got it right.
Almost, okay. Apologize if I butchered your last name.
Fine.
Presenting our GHG inventory from Building Washington State's Department of Transportation Roadways. Milad Ashtiani is a researcher at the University of Washington and a civil engineer who received his PhD from the University of Washington in the summer of 2022. Milad is responsible for the execution of research and analysis, development of guidance documents and educational resources and outreach across the design communities to improve the quality, accuracy, and effectiveness of building material. Let me see whether I read it across on it. Building performance tools, methods, and data that address embodied carbon. As a building and material researcher, Ashtiani works collaboratively with UW's Carbon Leadership Forum's internal research team, as well as with architecture and engineer firms and research consortiums across North America with a focus on building performance, computation, embodied carbon assessment, and life cycle assessment. Here's a preview of our upcoming seminars. And for those of you who are students at PSU, here are some upcoming events from the students in Transportation Planning and Engineering student group or staff. And as an overview of today's seminar, you can expect our speakers to present for about 45 minutes, followed by a Q&A. We'll be receiving questions through the Q&A features on your Zoom control panel, and we'll ask them at the end of the presentation. If we run out of time for all your questions, we'll give our speakers the opportunity to email written responses for any question left and unanswered. We have enabled closed caption, but you must click on the CC feature to view them. We'll be recording today's seminar. It will be available on our website later today, along with the presentation slides. If you're tracking professional development hours, this webinar is eligible for 1 hour of continuing education credit. With that, and we'll hand over to Milad.
Thank you so much. Hi. All right. Good morning, everyone. Thanks for having me here in Portland. Thank you all for making it here in person and those for watching us online. I'm really used to giving in-person presentation. It's been a while, so let me try this first. Yeah, it works. Yeah, it works. Back to normal. Again, thank you all for joining. And also, I want to thank Jordan Palmieri, my colleague at Lifecycle Lab, who made it here today. He's living in Portland, so I asked him to right here and stay with us. And if you have like any scorching questions I can't answer, I'm going to ask for his help. All right. So today I'm going to talk about one of the projects that I worked on when I first graduated and became a research scientist at Carbon Leadership Forum. But I'm going to talk about a few other things before we get to that project, because I think talking about just one project and all the technical things happen could become a little bit boring. So a little bit about myself. You can see my education was all in civil and environmental engineering for the most part. And I was doing pavement engineering when I was a master student at UMass. So I did a lot of testing on materials. So I became more familiar with materials, mostly on, again, asphalt binder and asphalt mixture, mixed testing and all that, because I liked working with equipment. And, that was my sort of introduction to sustainability and pavement and road engineering. And then I became more of a civil and environmental engineer during my PhD when I started working more with materials, more of concrete materials, actually. And then I got introduced to rating systems, sustainability, and life cycle assessment eventually. And then I got the pleasure of joining Carbon Leadership Forum right after my graduation. And I'm currently research scientist at Life Cycle Lab, which is a University of Washington entity. So just to clarify, we were a part of the university as Carbon Leadership Forum, and then we sort of split it up into a non-profit organization and a research lab at the university. And I listed a few of the related research projects I worked on, and by related, I mean, related to sustainability, life cycle assessment, and embodied carbon. And I'm trying to sort of talk about these as I'm going through my presentation, so I'm not solely focusing on one of the projects that we did for the Washington State Department of Transportation, or WSDOT. So you're going to hear me saying WSDOT, and by that I mean Washington State Department of Transportation. All right, a quick outline of what I'm going to talk about. So a quick background on climate change, sustainability rating systems, and why it matters. Hopefully, I don't really need to spend a lot of time on this. And then I'm gonna talk a little bit about embodied carbon, what embodied carbon is for those of you who are not really familiar with it, and also about life cycle assessment, which is the accounting tool for embodied carbon or other environmental impacts. And then I'm gonna shift to the project that I was advertised to talk about today, which was the inventorying of greenhouse gas emissions from roadway construction for WSDOT. And then if we have time, I'll see. I really didn't practice the timing today, but if we have time, I'm going to talk about what's happening now in the world of embodied carbon and life cycle assessment. So we'll see how much I can get. All right. Do I really need this slide? I don't know. Maybe not important. Climate change is real. It's happening. We have a ton of evidence. I'm not going to spend like 2 hours proving that it's happening. But what is probably interesting here is, as you may know, global temperature has a very high correlation with the amount of greenhouse gas emissions, in particular carbon dioxide, that we put out in the atmosphere. So it's evidently not the sole cause of rising temperature and climate change, but it is one of the most important. And also, buildings and transportation infrastructure materials matter. They dominate the raw material consumption globally and in the US by over, I would say, 80% of total raw materials that we consume. Steel and cement alone are responsible for more or less 15% of global greenhouse gas emissions. Again, global is the key here. It's a little bit less in the US. But again, big deals, steel and cement alone. Cement alone is thought to be about 8% of total global, energy consumption and CO2 emissions. So that's a big deal. And also on the policy side, we see like a surge of new policies coming that try to limit, the amount of embodied carbon that we put out in the atmosphere. And you probably have heard of Biden's BIL, or bipartisan infrastructure law, that put out a lot of research money to see, what we can do to reduce those emissions. And then, bike lane policies around the nation that are coming out. I think Oregon has it. Colorado started it. California actually started it. Washington is also starting to think about it, or actually it was passed recently, some sort of it. And they put some limits on the amount of emissions you can put out per material. They again focus on concrete and steel for the most part because they are the major contributors. And also put the city of Portland's low carbon concrete procurement policy, which again, these are just some evidence of these things are gaining more attention and gaining traction in the world of policy. So the solution to all of these things, if I want to put it very simply, is just sustainable thinking, life cycle thinking, and sustainable development. But it's like a mouthful. There's a lot going on into just this simplest statement. So I try to kind of uncover some parts of it that I spent time during the past few years. All right, so I'm going to narrow down the focus a little bit here to roadway infrastructure because we talk about infrastructure. I mean, buildings make sense. We know what buildings are. But when we talk about infrastructure, that's like a very umbrella term for a lot of things. We have transportation infrastructure, we have water and wastewater infrastructure, we have electrical infrastructure, we have like airfields, we have railways, we have metro. So we have a lot of different types of infrastructure. But my focus and my research really focuses on roadway infrastructure, which is again not just pavements. People in the roadway infrastructure world think of roads as just being pavements, but that's just the surface of it, literally and figuratively. If you want to just talk about pavements, you're just touching the surface of it. There's a lot going on around it, underneath it. You can see some of the labels here probably. Hopefully we can see them, but you can visually inspect them. We have sidewalks, curbs and gutters. We have a lot of pipes going underneath. We have sublayers. We have a lot of other things going on. So if you want to capture a good picture of what a roadway is, it's not just pavements. So I think that's just the message here. So this is sort of where my journey into sustainability and especially sustainable transportation infrastructure started. I started with rating systems, and I think it actually started for buildings as well. Building sustainability sort of got more traction when rating systems have started working. So how many of you have heard of LEED certification? So almost all of you, right? So it started, I think, early 2000 or late 21st century or 20th century. And then a little bit later, I would say a decade later, so the transportation infrastructure or roadway infrastructure industry is lacking. I mean, it's lagging behind a little bit from the building side. I mean, they're just following mostly how buildings evolve in terms of sustainability. And we at UW developed sort of one of the first rating systems for roadways and transportation infrastructure called Green Roads in 2009. And I was lucky enough to join the research team that actually developed this. So I started collecting a lot of data from them. I started looking at how sustainable roadway infrastructure will look like. And this is just one way of looking at what are the things that we look at or we're searching for when we talk about sustainable infrastructure or sustainable roadway. So you can see what I call is a scorecard. So there are some practices or sustainable practices from this rating system in particular, and there are more rating systems now that are alive, like the Invest or Envision, that are mostly from the federal government, but we're sort of using this scorecard as like a very insightful one. So a lot of these terms may be repeated in other rating systems, but the goal of this is to put things into numbers so that we can measure things. So this is kind of the main goal of a rating system. Just put some numbers into some things that we cannot really measure with like a ruler. so that we have like a common metric, so we can add them up, we can compare them. And as part of this, you can see, again, this is just an example of an actual old version of Green Rules. But you can see life cycle assessment and life cycle inventory, which are both terms related to mostly embodied carbon, but related to life cycle thinking happening here. And that's for a good reason. And the newer versions of these rating systems are actually focusing more on these two credits or two categories that I highlighted here. So what does a sustainable roadway look like? This is one of the projects I worked on before construction, or before a before photo, and here's an after photo. You can see a lot has changed. It was like a 2-lane, and now it's a 3-lane. It's wider. It has bike access. It has runoff flow controls on the side. It has sidewalks. So it has a lot of other features added to it. Some of them are visually visible. Some of them are not. Like the pavement here was reused. Like 80% of the existing pavement was reused, but you can't really see that, right? So life cycle assessment and some of the other tools that quantify things are very useful to uncover what's going on behind the scene and about the things that are not visible, right? So when you do a life cycle assessment, the numbers turn out to be lower for the case of reuse, for example, or recycling, or some of the other practices. But what it meant in practice, I spent hundreds of hours just extracting information from construction documents. And I don't know if you've spent time on looking at construction documents, but there could be like 1,000-page documents talking about how they built like a section of the roadway. It was not really fun, especially that, finding a particular number from like a 1,000-page document is tough. And since the projects were coming from almost all around the nation, the language and the codes are not really, consistent and similar. So some states might use one term for stating the exact same thing as the other state does. So it took me like, I would say 2-3 years to digest all this information. It was only for 33 projects. You can't imagine how harder it could get when we talk about like a state worth of roadways. And in particular, I started developing some what I called sustainable benchmarks for roadways. So there were a lot of like new parameters that I tried to introduce, and there were two that were of my most interest, which were carbon emissions and energy consumption from those projects. And I tried to sort of create those benchmarks based on the value of the projects. And I could have done this in different ways. But this was sort of my first initial attempt at trying to connect life cycle assessment and life cycle thinking and carbon quantification into something that policies can adapt and use to set some limits. So a little bit about embodied carbon, but before I begin, how many of you have heard of the term embodied carbon and know what that is? All right, great. So I'm glad that I put out these slides here because a lot of other things that I'm going to talk about that particular project relate to embodied carbon. So it's, I think, worth knowing the terms. So embodied carbon is the cumulative life cycle greenhouse gas emissions that are released during control, extraction, manufacturing, transportation, and installation, right? So for example, you can see all the beautiful concrete columns in this building. And you may think like how this thing was made from scratch, right? So, you extract the limestone and a few other, rocks out of the ground, you haul them all the way to like manufacturing facilities, you crush them, you make powders, you put them, you mix them, you heated them up in cement kilns, for example, to produce cement. For aggregates, for rocks, you basically just crush them. And then, you have to mix all these things together and then transport, the mix, if you're making ready to mix concrete, all the way to the sites. And then you have to, pour them somehow And then this process kind of continues happening during its life cycle, because, after a few years, let's say 20, 30 years, you have to come back and repair some of them. So that needs additional materials. And then once the building comes to its end of life, you have to think about what you want to do with the building. Do you want to tear it down all the way? Do you want to reuse them? Do you want to, recycle some of the materials and all that? So thinking, life cycle thinking is hard. It's not easy because you have to think about the future and what's going to happen in the future. And also you have to think about the past, what happened to the material prior to it getting here. And it's mostly an accounting practice to think about all of these, and also some thinking about what's going to happen in the future. So embodied carbon, as the name sort of now suggests, is all the greenhouse gas emissions that were produced during all these procedures and processes. And then I included this one because we usually seem to overlook another important aspect of carbon emissions, which we call operational carbon, which differs from embodied carbon, at least for buildings and roadways, and sort of the same way. So for buildings, it's usually about the energy consumption of buildings, how much electricity and how much heat you use to, make buildings livable. And for roads and transportation infrastructure, it can get even more complicated because, the users now become vehicles, and we know most vehicles burn gas to ride on the roads. So we have probably a whole other series of, research being done on traffic and transportation optimization and all that to reduce, travel time. So you reduce the amount of emissions. But those are just a little bit separate than what we're talking about here, which we talk about operational carbon and roadway infrastructure. So for roadways, it's usually just how you can maintain the road to be not livable, but drivable, right? So think about things like roadway lighting, traffic signals, heat island effect is probably one of the big ones that is, due to the amount of, heat that is absorbed by, hard surfaces on the road, which are, making urban environments a higher temperature, and also the fuel consumption of cars due to what we call pavement rolling resistance. So this is another big area of research that we'll talk about, especially when they want to compare alternatives, because, people say asphalt has higher friction, causes higher friction between tires and the pavement, so it increases the amount of gas that cars need to burn, and it's less than for concrete, and all those arguments. So I think the bottom line of this slide is that you cannot draw a whole picture of the embodied carbon of carbon emissions of a roadway or a building without thinking about both embodied carbon and operational carbon, and this equates to a term we call total or whole life carbon. But again, the focus of my presentation is not operational carbon. My area of specialty is not operational carbon assessment. And, I just thought it's important to know that it exists at the very least. So another way of thinking about greenhouse gas emissions is this sort of categorization. So it's mostly a greenhouse gas emission accounting protocol where it divides greenhouse gas emissions into 3 scopes. So scope 1, 2, and 3 are the terms that mean different things. So scope 1 are the emissions that are directly sourced from owned or controlled by the agency. Think about like the electricity that State Department of Transportation uses, or the amount of fuel that it uses to heat up its buildings. So that becomes scope 1 emission. And we have the scope 2 emissions, which are indirect greenhouse gas emissions from electricity generation that an agency purchases, right? For example, Department of Transportation may purchase electricity from different sources, and it has some control over which source to purchase electricity from, but it cannot control how the electricity is actually produced, right? So some control over the purchase, not any control over the generation of the electricity. And scope 3 emissions are basically everything else. And that's hard to digest because, you know, a lot of other things also happen. But for our case, scope 3 emissions are mostly about the materials that an agency purchases. And that relates to Department of Transportation's very much because, you know, they're not producing construction materials like asphalt and concrete. Rather, they purchase it, right? They purchase it and they just basically ask the contractor to manufacture it and, you know, use it on projects, right? And it's not directly under agency's control, right? Because agencies don't produce or manufacture those materials. And when I said, you know, this is a corporate greenhouse gas accounting protocol, it really very much applies to departments of transportation, and that's why it's now being used more frequently to account for greenhouse gas emissions. And then comes LCA. So how many of you have heard of LCA, life cycle assessment? All right, few of you. That's great. You know, you have probably heard of the term life cycle cost analysis, which is sort of the same deal, same way of thinking about accounting, but you know, life cycle cost analysis is mostly about cost, as the name suggests, and life cycle assessment is sort of the same way of thinking, but the measure here is environmental impact, and environmental impact or several environmental impacts. So it's a standardized methodology that helps us quantify environmental impacts again. And there are different, you know, standards out there, you know, from the US, from Europe. But in the US, it's mostly ISO 14000 series, 14040 and 14044. And what we really measure using life cycle assessment in terms of greenhouse gas emissions or embodied carbon is measured in units of carbon dioxide equivalence, which is basically a metric that combines different greenhouse gas emission impacts and how they impact climate change. And that's why we have this term global warming potential, or GWP, which is the measure, and the unit is CO2 equivalent. And you know, life cycle assessment divides up impacts into 4 different stages. A, B, and C. It's sort of chronological. So it starts with you know, A1 to A3, which are mostly about upstream processes that are used to produce materials. And then we have the construction phase, A4 and A5, which is about how you build things. You can think about like rollers and pavers that build the road, and the trucks that kind of haul all these heavy materials to and from the site. And then we have the use stage or B stage impacts, which are mostly about how you maintain and rehabilitate the road. And then we have the C stage impacts, which are all the processes and all the emissions that happen at the very end of a structure's life. It could be a pavement, it could be a roadway, it could be a building or anything else. And then we have module D, which is basically outside what we call the system boundary, but it's basically burdens and benefits you get from, for example, recycling and reuse and all that. So it's being accounted separately, but you know, those benefits and burdens should be accounted for. So we have also 3 terms that are very important here. Cradle to gates, as the name suggests, it's all the emissions from the material extraction all the way to where it's produced. And then we have cradle to grave, which sort of encompasses A to C impacts from the cradle, from material extraction all the way until you do something with the material at the end of its life. It could be landfilling, it could be recycling and all that. And then we have whole life carbon, which accounts also for operational carbon at the very bottom. So although, you know, buildings and roadways, again, use same materials, but the accounting practices are a little bit different between the two. And, you know, I talked about the operational carbon example, and, you know, embodied carbon is sort of the same. So for roadways, this is just a hierarchy of different LCAs you can run on a roadway. So you can just do an LCA for a product. Let's say the concrete or asphalt you use for a roadway. And that becomes a product level LCA. And then it could be expanded to include more products, the series of products that are used to build and elements of the roadway. We can think about like a pavement structure, we can think about sidewalks, we can think about curbs and gutters, which probably have a combination or a mix of different materials and products to be built. And then we have whole roadway LCA, which is basically all of the roadway elements that are used to basically build the whole infrastructure. It could be a combination of light poles, it could be pavements, curbs, gutters, everything that you think about, even the paints on the road and all that. So that becomes a whole roadway LCA. And then we have EPDs that you have probably heard of, but EPDs are becoming standard practice in reporting life cycle assessment results. They are not usually cradle to grave, and these are mostly cradle to gate impacts, as they call them, as I defined them earlier. And these are following standard documents called PCRs or product category rules. So they outline the methods and the standard methods to be followed to do the LCA. Because there are many ways you can run an LCA. And without a standard, everybody can do it on their own way to advertise for their own product, but just to basically turn around that and have like a common ground for everyone to follow rules. PCRs are developed, and they're being more and more used in policy making and accounting practices and all that. And once you have a collection of EPDs and also some of the production volumes, because EPDs are just per unit of a product. Let's say what's the carbon footprint of a cubic yard of concrete, and if you know how many cubic yards you use in your building, you can do some simple calculations to find out the total. And then then afterwards you can set benchmarks, thresholds. Cities usually do that. Agencies, state agencies, federal agencies do that to set the standard, set the threshold, so that everybody has to be below some limits. So if you want to learn more about embodied carbon, we published a 3-chapter series or 3-part document on embodied carbon. If you like, you can scan the QR code. It directs you to the website where we have these. And it was basically my attempt of summarizing all of these things into a very short document. So I probably recommend you taking a look at it if you have time. And with this rather long introduction, I'm going to dive deeper into how you can do carbon accounting for a state DOT's worth of roadways. I tried to kind of separate the background from this so that now I can dive deep into what happened there with just a little bit of a background again for this one. So, as I mentioned, the real problem is climate change. We're not going to argue about that anymore. And the more recent problems or issues or things that got the State Department of Transportation thinking about embodied carbon accounting is the amount of federal and state level policies that are now requiring greenhouse gas emission reductions, and also some new thresholds that are coming out so that states and contractors have to adhere with. Most of the transportation agencies have like a near net zero emission by 2050. A lot has been focused on clean fuel, clean energy, and all that. And we sort of are trying to achieve that. Electrification is probably a big deal in this decade. But people also started thinking about the materials because it's really hard to decarbonize the material or industrial emissions. It's really hard to change or upgrade a whole cement plant. It doesn't really happen overnight. So we have to think about it ahead of time, and we have to prepare for it. So the focus of greenhouse gas emission reductions, as I stated there, has been focused on the scope 1 and 2 emissions, the things that are related to electricity and fuel. for the most part, right? And we started accomplishing some of the goals there, which is really great. But also we started realizing that highway construction and maintenance uses a lot of materials, and those materials come with emissions. So that was sort of the background that we started, talking with Washington State DOT, and we said, why not, doing like a study to see how much emissions you produce from building and maintaining your roads. And we can just take a look at your data for the past few years to try to figure this out for you. And a few state DOTs actually attempted this. Actually, Oregon DOT was probably one of the first states that has done this. So we followed their work a little bit, and we're in touch with Oregon DOT a lot to find out how they did it. And California also did it a few years back, but not as comprehensive as how Oregon DOT has done it. So there were just a few states, and there are still just a few states that have done it and know in a ballpark amount that how much emission they produce. So we narrowed down the focus to upstream scope 3 emissions, basically A1 to A3 emissions in an LCA perspective. So we're trying to figure out the emissions from the materials production all the way to when they are constructed or they're used in an actual roadway. So a few of the research questions, I think I went over all of these, but our overarching questions were, how can we quantify greenhouse gas emissions? We knew that we're going to use life cycle assessment, but we're wondering what amount of data is available and what data is available for us to use. And then at the end, how can we recommend to make the process better and smoother, make the data collection more efficient, and at the end, think about ways that we can use these data and these analysis to reduce embodied carbon in the future. So we try to propose sort of what we call a decarbonization roadmap for WSDOT, or the idea of it. We didn't really expect them to implement it right away. But just having an idea of how this can be produced and thought about was our goal. So we limited this study to 2017 and 2021, and we all know that COVID also happened during this time period, and that was one of the reasons why we expanded it to include 5 years, because we all know that the amount of construction really was reduced during the COVID time, and we can actually estimate how much it was reduced. It's sort of cool to see the effect of COVID on our results too. So we started collecting data. So everything at the end, when you want to do the actual technical analysis, comes down to data. So we conducted a lot of interviews with WSDOT folks to the point that they were really tired of us, because I was just bugging them every week of where can I find this, where can I find out this database is not working, why don't you have this data in the data set, why are you like organizing your data this way? I started questioning and digging into their system, which was pretty old. So you should know that state DOTs are a little bit old school. It's not like the building industry where they might have like Revit models of a building. There is no such thing. You have to dig really deep into like construction drawings and plans, which are really boring to look at. But they actually had some amount of good data too. So I give them that, especially when it comes to what I call bid tabs or pay item lists. So I would say most states, if not all of them, have such a system, such a data set that keeps record of the amounts that were paid to build the job. We don't have such thing for buildings, because buildings are for the most part not public, and these are just public data, public information, because these are public roads. We all drive on them. The state owns them, and they own the data too, right? So this was probably the backbone of the data that I was looking for. And I explored, pay item lists during my graduate years for like 4 or 5 years. So I was pretty much familiar with the terms that, basically contractors asked for to be paid. You can see like roadway excavation, for example, You see traffic control as a pay item, and this list can go on and on. So for like I would say a $10 million project, which is sort of a typical roadway construction project, you probably see like probably 120, 150 pay items, right? And you can imagine for a whole road network of roadways in a state, this list can grow and grow. So I started digging data for the past 5 years, from 2017 to 2021, and I found that there were about 609 contracts that were actually working during that time period. It was probably a little bit lower on an average basis because, again, of COVID. So I started collecting these data, and I mean, again, this is publicly available, so you can just go to WSDOT's website and search for unit bid analysis, and you can find all this. But that was not really sufficient. Although they had good records of some material quantities and some pay estimates, they were not final quantities, meaning that they used those pay item lists to bid projects and award them the projects, right? So there were some challenges in that because those numbers were mostly estimates. There were not final quantities from the projects, so we didn't have like actual numbers. But in my opinion, it was enough for us to start estimating. But we also leveraged from a lot of other data sources that were really pretty much scattered across different databases and data sources and offices at a state DOT level. And it was hard to find out which office really manages which data set because they were all scattered. Again, some offices had like data sets that the other office also used. And there were sometimes 2 different data sets to keep the same thing, same amount of data. And sometimes they did same data that they had didn't match. So a lot of challenges in figuring out who's right and who has the best data. And it all came down to knowing one person who knows all the data sets. And we actually had that link to that one person, and she really helped us kind of understand the mechanism behind all of these, and she really helped us point at the right person. And it was just one person, one engineer who was managing the data, and we were like lucky enough to connect with them through a lot of connections. I was a grad student at UW. I'd worked with WSDOT before. My advisors were also working with WSDOT for like 30 years, so I have good connections to find the right persons. And it boiled down to this data, ecosystem. So all these data sets, I'm not going to talk about all of them, but they kept different things. You have probably heard of pavement management system data, which stores all the actual quantities of materials that were used to maintain roadways. They had another good data set called the statistical analysis of materials, which, as the name suggests, they had some more data about like even different lots that they paved the roads in. So good stuff here, but again, hard to bring them all together. And that took me almost a year again to pull these all together. And then based on the data that it collected, which was, again, based on the unit bid analysis data, pay item lists, I built a lifecycle framework on that because, we don't have much of an LCA tool for roadways, or at least by the time we didn't have such a thing. So I started to, again, build it from scratch and apply, the concepts myself. So it was mostly a spreadsheet format that I started developing, and it was, again, based on the pay item list data. I used several different types of data sources other than material quantities that I collected from WSDOT. So LCA has 2 main parts. One is how much material you use to the smallest, decomposition possible. For example, if you have like a concrete mixture, you want to know how much cement, how much aggregates, how much water, how much admixtures, and a lot of other things were used in the actual concrete. And you also want to know the environmental impacts of them, right? So that's when life cycle inventory comes to play. It's a data set of environmental impacts from all of these materials, right? For example, for cement, we have different types of cement for sure, but life cycle inventory data has information about, let's say, CO2 footprint, methane footprints and a lot of other different emissions footprints in them. So I started collecting quantity data from WSDOT, and also from several sources, I started digesting and collecting life cycle inventory data. So that in simple words, we can multiply these two together to find out the total carbon emissions. So I took two approaches. I'm not gonna, again, dive deep into like the calculation here, but the math is sort of simple. It's mostly linear algebra, a bunch of multiplications, but you have to consider different things. For example, for transportation, you have to consider transportation distance and types of transportation, usually trucks in our world. And then, emission factors for like fuels and, gasoline, diesel and all that. And it's the same for like construction equipment, like rollers, pavers, these things that actually build the road, and also materials. So when you add them all together, you have a full picture of A1 to A5 impacts or cradle to construction impacts. So the first approach I took was simply this, right? So I had this list of life cycle inventory data, and you can see sort of this spread of numbers that I found, and this is logarithmic scale. I'm not going to talk a lot about this, but you will notice some numbers are on the lower side and some numbers are on the high side. So on the lower side, we have like aggregates, rocks that are not really energy intensive to produce. And on the higher end side, we have higher energy intensive materials like aluminum, like, plastics, these are the things that have higher carbon footprints. So this was the first approach, multiplying these factors, which I call emissions factors, by material quantities to the finest resolution possible. But the problem was we didn't have data for all of those 609 contracts. Especially if you're familiar with contracting, we usually have two main types of contracting: design, bid, build, and design, build. So as the name suggests, design, bid, build goes through a bidding process, and so the name bid tabs or pay item lists, right? For projects that don't go through the bidding process, which are design, build process, they don't have that pay item list in WSDOT's database. And those projects seems to be or tend to be huge projects. Like we had a $500 million design build project or $1 billion design build project. So it was a big miss if I missed those, right? Because they contributed to about like 40–50% of total DOT's or WSDOT's budget, but I didn't have any data for them because they were just huge and they were design build projects. And that's why I took a second approach, which was mostly a math game for me. So I've done some sensitivity analysis to try to estimate footprints of those projects. And how I did that was to develop what I call an economic-based emissions factor. So I collected all those data for the projects that I had data for, and I started using those life cycle inventory data to estimate projects' footprints. And then I thought about like how does cost correlate with those emissions? And I've done like previous studies, prior studies to this, to figure out there is actually a high correlation between cost and the amount of emissions. We all know that, we pay for the energy, right? And energy comes with CO2. So the idea was not really a bizarre idea, but to know how exactly the correlation is was the key here. So I started developing some economic-based factors by simply dividing, the total bid price of the project or price of the project by its total carbon footprint, right? So for each project, I had that number. For example, some amount of CO2 per $1 million spent on that project. So I started creating, these factors, and you can see sort of the box plot of it, the spread of it, and it's skewed. It's not totally normal, but it was a good start for me. So I assigned these factors to all the projects, right? Especially for the projects that I didn't have any idea about their materials. So I started assigning these randomly to different projects, and I did this for like some amount of iterations, like 10,000 as I stated here. And I followed more Monte Carlo simulations. I don't know if you've heard of this, but transportation folks are probably more familiar with it than I am. But that was my way of like thinking about missing data, using the data I have and running some sensitivity analysis and using math to figure that out. And I think I was sort of successful in doing that. Because the emission factors, first of all, were not really scattered. The economic-based factors, and the actual numbers at the end really made sense.
We're wrapping up in about 10 minutes. It'd be great if you start to wrapping up and then we leave a few minutes for questions.
Of course.
Thanks.
Yeah, I think these were the most time-consuming parts because methods are really hard to talk about without diving deep. But jumping into some of the results. So this is what I got. These are total carbon footprint estimates and those that I was able to measure. So there are two key parts here. One is basically these black boxes, and the other part is the solid boxes. So solid boxes are the ones are for the projects that I actually had data for their materials, and the blank boxes are for all my estimates, right? So the rest that I estimated, which seems to be actually a big deal because, again, as I said, design build projects were a big part of state DOT budgets, and these mostly present those, these empty boxes. And you can see like the breakdown of different material contributions. So you can see, asphalt and concrete kind of pop out, as you can see. So I tried to use actually asphalt and concrete colors, so hopefully that's helpful. And the rest that I estimated, it's good that I was able to estimate, but the problem was I didn't know the contribution of different materials to them, right? I found the totals, but I didn't know what would be the contribution of separate materials. And you can kind of see the slowdown of construction material consumption, especially at 2020, and that's evidently the effect of COVID on construction. It almost probably halved the amount of money and the amount of emissions as a result. And you can dive deeper into the results. So I broke down the impacts by different construction categories. What I wanted to point out here is that pavements actually matter more since they contribute to about 50% of our roadways carbon footprint, at least the amount of carbon that we can account for using LCA. And also another way of looking at the data is to break it down based on these three different LCA stages. A1 through A3 again is the material production and extraction stage, which contributed to about 85% of total emissions, which is followed by material transportation, basically trucks that haul all these heavy materials, and construction plays a rather smaller role in here by contributing to about 4 or 5% of total emissions. Then I tried to put things into perspective because those numbers were really abstract. I found that on average, WSDOT consumed or produced about 300,000 metric tons of carbon. But what did that mean? So I started asking for data from the Department of Ecology, who tracks, who keeps a better track of some of these carbon emissions, especially at the scope 1 and 2. So I asked them for data for that 5-year span, and this is the total emissions from scope 1 and 2 that Department of Ecology was able to capture. And you can see ferry fuels kind of play a big part in Washington because Washington has the largest ferry system in the US, and I think the second largest in the whole world. So you can imagine a lot of fuel being used to drive those. So I put these numbers together to do a side-by-side comparison. So you see the middle bar is the one that I estimated, and the one on the left, which is in reddish color, is the one that I found from Department of Ecology. So scope 1, 2 emissions versus scope 3. And we can clearly see that scope 3 emissions are comparable to the scope 1 and 2 emissions, and for the most part are higher. So that was the point that I was like seems like the method I kind of developed and the data I use sort of makes sense. You know, when you put numbers together, it's not like an order of magnitude difference. There were really close numbers. And again, it suggests that, you know, Scope 3 emissions were actually larger on average. So we started digging into the literature to find out how we can now use these data to inform some of the policies and suggest some decarbonization strategies. Because we had the data to kind of implement these strategies. And then I came up with this list from the review to find out how can we reduce emissions from these material categories or from these construction categories that I tried to actually look at in my LCA. And these are just showing ranges of possible carbon reductions per strategy and per material. For example, we have like asphalt recycling at the very top with the potential reduction in carbon. We made some assumptions on how to implement these and what would be the market absorption of all these, like how many contractors are actually going to use recycled materials and all that. I put these all into numbers and some scenarios because it becomes scenario based, like how aggressive you want to recycle. These are just some hypotheses or assumptions that we can make. So I came up with a list of 5 scenarios, becoming more aggressive as I go. Like scenario 1 pretty much depicts the business as usual, and scenario 5 is the decarbonization scenario, as they called it. And then I started applying all these reductions into the LCA framework that I developed. The beauty of this was that I had access to the data. I could do whatever I wanted to the emission factor data, the quantity data. So I applied all these strategies into that framework and that data. And you can see, how aggressive, the scenarios are getting. And this is probably one of my favorite charts out of that report that shows the near net zero decarbonization scenario where you implement most aggressive scenarios to get to near zero. It's real hard to get to actual zero here, but you can see the baseline, and I showed it in percentage because it makes more sense instead of just talking about just numbers, pure numbers. And you can see, asphalt and concrete sort of stay at the top, and recycling practices also stay at the top, like using recycled asphalt materials and supplementary cementitious materials sort of are the biggest deals. And we had some recommendations at the end, like we set some targets for WSDOT to follow and how to get to near net zero by 2050. And some other suggestions on how they can improve their database ecosystem and what additional data they need to collect and what research they need to support. And I'm glad that it's actually happening these days. So to sum up here, in this project, we developed a life cycle assessment framework for WSDOT to estimate your Scope 3 emissions. Our estimate was about 300,000 metric tons of CO2 equivalent per year, which is equivalent of, I think, maybe a little bit less than 100,000 cars driving a year. So that's actually a big number, right? And we showed that Scope 3 emissions, upstream Scope 3 emissions are at least as significant as Scope 1 and 2. We found asphalt and concrete are the biggest deals. So we start with asphalt and concrete and probably steel materials to begin with. And then you can think about more advanced strategies to decarbonize. And if you want to read more about this, it's on our website. There's also a summary report. If you don't like reading a 130-page document, we wrapped it up in, I think, less than 10 pages. It has most of the information. So go check that out. It's on our website, and here's the QR code for that. And I'm gonna skip this part because we're running out of time, and I saw this comment. So I'm just gonna go to the last slide here and say thank you for your attention. And yeah, that's it. Thank you.
I think we are at time, so probably have one question from those of the room. For those of you online viewing on Zoom, we will capture your questions and share that with Milad, so he might be able to provide a written response. Gabriel.
Thank you. My name is Gabriel Quiñones. I'm a PhD student in urban studies. Thank you for your presentation.
Thanks.
I had I'm not an engineer. My background is in planning, so I might be not familiar with all the technical concepts. But when you were talking about, for example, comparing, because it's based in Washington, right? So you talked about the ferries, right, and the difference that could make from other places. I wonder if, from your experience doing this, if you would have done it in a place, if weather is an issue, you think the weather would change your results in some way, like you were done this instead of Washington, let's say more to the south or more of in a place where it's warmer or more humid? Do you think you will see difference in terms of asphalt and concrete and in terms of the cost of everything? I know it depends how you have to do it, but I wonder from your experience, if you think the weather could alter that and maybe have a lower or higher footprint at the end.
Sure, great question, actually. Yeah, we thought about this too. So scope 1 and 2 emissions in Washington, as I said, comes mostly from ferries. And I would assume that this number would be actually smaller, a smaller share in other states that don't have a ferry system or they don't like burn fuels a lot. In terms of like contribution of different materials, I would guess that it's going to be sort of the same, and actually it's sort of matched with the Oregon's DOT, Oregon DOT's study and also California's study. So we did some sort of a comparison between them, and we sort of validated this. But you know, the contribution of different things, like you know, material transportation might be a bigger deal in Texas, right? Because that's a big state. Transportation, you know, takes probably a larger contribution. So when I talked about like the breakdown of materials versus construction versus transportation is probably a bigger deal. And you know, for some other states, you know, every state is different for sure. But just to bring up some examples of how the differences can be, you know, we looked at Florida as well. So Florida ships aggregates or rocks all the way from Canada. So you can think about like the amount of fuel that they burn to just to get the good aggregates from another country, right? So we can expect that it's actually a bigger deal from the asphalt and concrete side for a state like Florida, right? So there are some differences, some nuances, but we think that scope 3 emissions are actually going to play a more critical role in other states than Washington. And just to maybe point out some other thing to wrap it up. You know, Washington is actually pretty much diverse in terms of weather or climates, right? So on the east side of the Cascades, you know, we have like harsh environments, very cold environments, and on the west side we have more of a chill, you know, environment than humid. So there are some differences there, and we actually saw some differences in like transportation distances and the type of materials these two use. So I would call Washington as a good case study example because it has a very diverse climate. Thank you. Sure.
Great. Okay, thank you all for attending today's seminar. For those of you joining remotely after the seminar ends, you will have the opportunity to complete a brief survey about today's events. That should only take a few minutes of your time, and appreciate your feedback. Thank you, Milad, and thank you all for joining today.
Yeah, it's a pleasure.